Okay, so before we start our video today, let's look at this warm-up question for today. This is for 1014 and for 1015. And the warm-up question says, which of the following is not true regarding Newton's first law? Okay, so take a look at these answer choices and see if you can answer this question. Which of the following is not true regarding Newton's first law of motion? Okay, so just to kind of refresh your memory, Newton's first law of motion says that an object at rest remains at rest, and an object in motion remains in motion at constant velocity unless acted upon by a net force. Okay, and so in the last video we talked about Newton's first law, and we kind of wrote it out as a flow chart that you should have in your notes. We did some examples with Newton's first law. We broke it down like piece by piece to understand the concept of the first law. And so with that in mind, let's go through these answer choices. Okay, so answer choice A says an object can move at a constant speed with a zero net force. Okay, so Newton's first law says an object in motion remains in motion at constant speed along a straight line, unless acted upon by a net force. That means an object can move at constant speed in a straight line as long as there is no net force. That means as long as there is a zero net force. Okay, and so A is a true statement. Okay, B says a constant net force is required for an object to remain moving. Okay, that statement is not true. Okay, and so B is actually the correct answer to the question. A net force causes an object to accelerate, to change its velocity. It's not required to remain, or for the object to remain moving. Okay, C says if an object experiences net force, that object must change its velocity. Okay, that is true because, again, going back to the first law, it says an object in motion remains in motion at constant velocity unless acted upon by a net force. Okay, so what that means is if there is a net force acting on an object, that means that object's velocity must change. And so C is a true statement. And then D says an object can remain motionless with a zero net force. That is also true. Okay, that's the object at rest remains at rest part. Okay, and just to remind you, net force, we write F net for net force. Okay, this is the sum of forces. And so this is the quantity that you get when you add up the forces acting on an object, not add up the numbers, but you have to take into account the direction as well. And so if you have two forces going in opposite direction, they kind of cancel each other out because one force would be a positive force and the other force would be a negative force. Okay, so when we talk about net force, that's what we mean. We mean the sum of the forces acting on an object. Alright, so let's move on. We kind of went over Newton's first law already, but here it is again. Okay, so in today's video, we're going to talk about some general forces and how to draw what's called free body diagrams, which is something we're going to be doing for the rest of the unit, so it's kind of important that you know how this works. Before we get into free body diagrams, let me tell you about the most common forces that you will see in this class. Okay, so these are forces you should know. I would highly recommend that you add these to your notes because you're going to be dealing with them all the time. And you need to be able to recognize when these forces are present in a problem based off of the context given to you in the question. Okay, and so again, I would highly recommend you add this information to your notes. So pause it here if you need to do that. Okay, so let's talk about some of the more common forces that you might see in this class. And there's lots of different forces that we're not going to talk about. These are just the most common ones. Okay, so the first one is what we call weight, aka force of gravity. Okay, so for force of gravity, we write F, G for force of gravity, and that is what is known as weight. Keep in mind, remember that force is a push or a pull, and that's measured in newtons. Okay, so we have the force of gravity. The force that holds a string or rope together is what's called the force of tension. And so one very easy way to recognize whether or not you have tension in a problem, if there's a rope or a string in the problem, there's probably a force of tension. So you would write Ft for the force of tension. Okay, that's the force that pulls along the rope or pulls along the string. Okay, in some problems you'll see friction, which we write FF for friction. Friction is caused by basically two surfaces or two solid objects rubbing together. The most important thing to remember about friction is that it always acts to oppose relative motion. Now that is basically a very fancy way of saying whichever way the object is moving or trying to move, friction acts in the opposite direction. Okay, so if I try to push a box to the right, then friction would act to the left. If I try to push a box to the left, friction acts to the right. Okay, basically always trying to stop the object from moving. Okay. Another very, very common force that you see all the time is what's called the normal force. Okay, so we write Fn for normal force. So in what situation do you have a normal force? Well, the normal force you have anytime you have a surface involved in a problem. It is the reaction force of a surface from something pushing on it. Here's an example. Let's say you press against the wall. You put your hand on the wall and you press into the wall. The force that's pushing back on your hand, that's the normal force. Okay, that's the wall pushing back on you because the wall is a surface. When you stand on the ground, okay, gravity pulls you down. The force that pushes you up, that stops you from falling like down into the earth, that's the normal force. Okay, so you have a normal force anytime you have a surface. Why do we call it normal force? This is just like a minor fun fact, but the word normal in mathematics means perpendicular, which is why in the notes you see on the right side it says any object which is touching a surface will experience a normal force perpendicular to that surface. Perpendicular just means it makes a 90-degree angle, a right angle, and so that's why it's called normal force. Okay, so when you press against the wall, if you push your hand like into the wall, the normal force comes back out from the wall at a 90-degree angle to the wall. Okay, so normal force you have anytime you have a surface. And then applied force is just like a generic force for like if I push on something, I would call that an applied force. I mean, I could call it like F push for pushing force, but we just say applied force just as like a generic term for a person or an object applying a force. Now, are these all the forces you're going to see? No, but they're most of the forces you're going to see. Sometimes you see forces where you don't know really what to call them, and so you just label them something that makes sense. Okay, so for example, if you had a problem with like a rocket ship, and there's a force from the rocket ship, you could label that like F rocket. Okay, just something that makes sense. Forces other than the ones over here can be indicated using subscripts. Okay, if I punch like a hole in the wall, I could label that force like F punch. Just some type of subscript that like makes sense in that situation. Okay, so if it's not one of these more common forces, you can label it anything that makes sense. Most forces you're going to see most of the time are one of these 5 forces. Now, how do you know which forces you have in a situation? Okay, well, if you look at the right side, I try to give you context clues over here, which is why I said before I would highly recommend adding this to your notes. Okay, because this is kind of a guide to when do you know which forces are acting on an object. Okay, so first of all objects, as long as they're not in space, all objects near the surface of a planet have a force of gravity. Okay, so when we're drawing free body diagrams here in a few minutes, you should, unless it says it's in space, you should probably start with the force of gravity because that's the one that you know has to be there. Now, I shouldn't have to say this, but the force of gravity acts down. Okay, so when you're drawing the free body diagram for the force of gravity, you put the arrow pointing down. Okay, the second bullet point says any object which is touching a surface will experience a normal force perpendicular to that surface at a 90-degree angle to that surface. That's what perpendicular means. Okay, objects touching a rope or string will experience a force of tension. So if you read like tension, or if you read like rope or string, or if there's a picture, if you see a rope or string, there's probably tension. Objects on a rough surface, or like a concrete surface or a gravelly surface, can be assumed to have friction. If you have a problem on like the ice, or it says it's a smooth surface, you can probably assume there's no friction. And forces other than these can be indicated using subscripts. Okay, so pause it there and make sure you have that in your notes. Okay, so let's talk about drawing free body diagrams. Okay, a free body diagram is like a lot to say, and so usually we call these FBDs. Okay, so FBD, free body diagram, is just a picture that basically shows the size and the direction of all the forces acting on an object. Now, I cannot stress this enough. A free body diagram has nothing to do with which way an object is moving. Okay, you cannot look at a free body diagram and know which way an object is moving. Okay, if I look at this free body diagram right here, for example, I don't know that this object is moving to the right. Okay, that's not the purpose of a free body diagram. All I know is that there's 4 forces acting on this object. Each force is indicated by an arrow, and the one to the right is the longest of those arrows. Okay, that means that's the strongest force. Okay, and so what I would say looking at this free body diagram right here is I would say that there is a net force to the right, but that does not mean that the object is necessarily moving to the right. How do I know there's a net force to the right? Remember, you get the net force by adding up all the forces. And so if I were to add this arrow to this arrow, you see how they're the same length but in opposite directions? Those two would cancel out. If I were to add this force, which is to the right, and this force to the left, this arrow is longer, so that one would win. Okay, so that means the overall net force would be to the right. Okay, that means according to Newton's first law, this object is going to accelerate to the right. Okay, so the length of the arrow on a free body diagram is important. But again, an FBD has nothing at all to do with which way an object is moving. All it does is tell you which forces are acting in what direction and their relative size. So, how do you draw an FBD? Well, you draw a dot to represent the object. If you want to know why a dot, just so you don't spend a lot of time drawing a pretty picture because it doesn't really matter that much. Okay, so you draw a dot to represent the object. Next, you determine which force or forces are acting on the object based on the context of the situation. Now, how do you know that? Well, you would go back to this slide over here that I told you to add to your notes, and you would look through your list and figure out, which of these forces are acting in the situation. Then, once you know which forces are acting, you're going to draw arrows going away from the dot. I don't know why it says box, it should say dot. Going away from the dot to represent the forces on the object, making sure to draw the length of the arrow appropriately. This is where Newton's first law applies. We'll do some examples so you understand what that means. But basically, when you think about Newton's first law, if the object is at rest, or if the object is moving at a constant velocity, that means you have to draw the free body diagram with a net force of 0. Okay, and I'll show you what that means. We'll do lots of examples with this. Okay, and then you correctly label the forces using subscripts. Okay, so this FBD right here on the left is pretty nice looking, but there's no labels on it. Okay, this one over here, they draw a box here instead of a dot, but it's still an FBD. Here you can see that the force is labeled. When I look at this FBD, by the way, notice how all the arrows look like they're the same length? That means I can tell that the net force on this object is equal to 0. Because if I were to add up all these forces, remember, the longer the arrow, the bigger the force. If I were to add up all these forces, they would all cancel each other out because they're going opposite directions and they're all the same size. What does that mean if the net force is 0? Well, in the last video we learned that means one of two things. Either the object is moving at a constant velocity, or it's at rest. Okay, so keep all that in mind as we're doing these FBD examples. Okay, so we're going to start off really basic. Example 1 says a book is at rest on a tabletop. Diagram the forces acting on the book. Okay, so step 1. Draw a dot to represent the object. I already have a picture, so I guess I didn't really need to do that, but there we go. Step 2. Figure out which force or forces are acting on the object based on the context of the situation. Now remember what I told you a few slides ago, as long as you're not in space, all objects that are not in space have a downward force of gravity. So I'm going to write down Fg, that's on my list of forces that must be acting. Then in my head, I'm going through this mental checklist in my head. Is there a rope or a string? No. Okay, it doesn't say anything about a rope or string in the problem. That means there's probably not tension. Is the book trying to move? Well, it says it's at rest, which means it's not moving. But is it trying to move? If it's moving or if it's trying to move, there could be friction. Okay, but if it's not trying to move, there's no friction. Is there a surface? Yes. What is the surface? It's the tabletop. Anytime you have a surface, you automatically have a normal force, Fn. By the way, don't confuse Fn, which is normal force, with Fnet, which is net force. Two completely separate things. And let's see, is anything pushing on the book to make it move? No. Okay, so the only two forces acting are Fg and Fn. Now, force of gravity always acts down. Okay, so I draw an arrow going down, and I label that Fg to represent the force of gravity. Now, a couple things. Number one, if the book is at rest, think about Newton's first law. An object at rest remains at rest, blah, 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 unless acted upon by a net force. That means if this book is at rest and remaining at rest, that tells you that the net force on this book, F net, must be 0. Okay, because, well, Newton's first law. That means when I draw the normal force, I know gravity goes down automatically. When I draw the normal force, it has to be going up, and it has to be the same length as Fg in order to cancel out. Okay, and so that's what my free body diagram would look like. Okay, the lengths of the arrows is important. The labels are important. Okay, that is my free body diagram. Okay, so pause there if you need to look at that some more. Okay, so let's do some more examples. Try to go a little quicker. An egg is free falling from a nest in a tree. Neglect air resistance. Draw free body diagram showing the forces involved. Okay, something you need to know. We've actually mentioned the word free fall before, but that's actually a term that you need to know. Anytime an object is in free fall, that means that the only force is Fg. Okay, that's a technical physics term. An object in free fall, by definition, the only force is the force of gravity. Alright, so what does this FBD look like? We draw a dot for the egg. We have an arrow going down. Label it force of gravity. Boom. We're done. Okay, now if I look at this FBD and I say, what does that mean? Does that mean that the egg is falling down? No, not necessarily. Now, it is falling down in this situation, but remember an FBD doesn't tell you which way an object is moving. All it tells you is which force or forces are acting on that object. And in this case, the force of gravity is acting down, which means that this object is going to accelerate down. Okay, so pause it there if you need to look at example 2 some more. Alright, example 3. We have a flying squirrel, and it says a flying squirrel is gliding. I would show you a picture if I could, or a video if we were in class. But it's gliding from a tree to the ground at constant velocity. And this is a really important context clue right here, constant velocity. Think about Newton's first law. An object at rest remains at rest, or an object in motion remains in motion at constant velocity unless acted upon by a net force. So the fact that they tell us it's gliding at constant velocity is a context clue telling us that the net force is 0. Okay, just something to keep in mind. Consider air resistance. If they say consider air resistance, that means, hey, there's air resistance. Alright, so I'm labeling out my forces. I always start with gravity. The flying squirrel's not in space, so I know I have force of gravity going down. I run through the checklist in my mind. Is there a rope or a string involved? No. Is there a surface? Okay, there's not a surface here. You might say the tree, but in this situation, the squirrel's already jumped out of the tree. When he jumped out of the tree, there was a normal force, but as long as he's flying through the air, there's no normal force because there's no surface. Is there friction? No, because there's not a surface. Alright. But there is air resistance, and we know that because it literally says that in the problem. Now, that was not one of the forces I listed before, so I'm just going to call it F air for air resistance. what does my FBD look like? Well, I know force of gravity is going down, and I know that if the net force is 0, and there's only 2 forces acting, I have to draw the air resistance force in a way that it cancels out the force of gravity to give me a net force of 0. Okay, so that is going to be drawn up, same length. Okay, the length is important. And there's my FBD. Okay, so that is example 3. Pause there if you need to look at it some more. Alright, let's just do a few more quick examples. Okay, problem 4 says a rightward force is applied to a book at rest in order to move it across the desk. Consider frictional forces. Neglect air resistance. Construct a free body diagram for the book. Okay, so draw a dot. Start labeling out the forces that must be acting. Force of gravity, book's not in space, so I know there's a force of gravity. Okay, is there a rope or a string? No. Is there a surface? Yes, because it's on a desk, so that means there's a normal force if there's a surface. Okay, it says a rightward force is applied, which means something is pushing the book to the right. I'm going to label that FA for applied force. And it also gives me a hint that, hey, there's frictional forces. So I'm going to have friction as well. Now, how do I do this FBD? Alright, so let's think about this. Force of gravity goes down. Check. Normal force is always perpendicular to the surface. Okay, so that is going to be acting up. That's going to balance out the force of gravity because the book is going to move to the right. It's not going to move like down through the desk, so the normal force keeps it from falling through the desk. Now there's an applied force going to the right. So I'm going to draw an arrow to the right and label that FA. Now, is the book accelerating? Well, to be honest, this is kind of an ambiguous question because it doesn't say if it's, speeding up or not. I'm going to infer from context it probably is accelerating because the book was at rest, and if it's being pushed, it's probably going to speed up. That tells me that the applied force has to be drawn longer than the force of friction. Now, why is that? Well, remember, an object in motion or an object at rest remains at rest unless acted upon by a net force. So if it's going to speed up, that means that the net force is not equal to 0. And so I need to draw this so FA is longer than FF. If it was being pushed at a constant velocity, that would be different. Okay, if it was being pushed to the right at a constant velocity, then I would draw these arrows the same to give me a net force of 0. Okay, so pause there if you need to look at that some more. Alright, so we're just going to do one more example and then you can get to your practice worksheet. A car runs out of gas and coasts to a stop on flat ground. If you don't know what coasting is, that's where you run out of gas and the engine doesn't apply force pushing you forward anymore. So you're still moving, but you're kind of moving on inertia. Okay, the car is like basically dead. Alright, so here's a dot to represent the car. It coasts to a stop. That means it's slowing down. I label out the forces acting on the car. Okay, force of gravity, that's an automatic one. I run through the checklist in my mind. Okay, so there's no rope or string, no tension. Is there a surface? Well, it's on the ground, so yeah. So that means there's a normal force. Is there friction? Well, let's think about this. Nothing is making the car move, but the car is still slowing down. So, yeah, probably friction. That's what's making it stop. Is there a force from the engine? No. Why? Because the car ran out of gas. Is there an applied force? No, there's nothing applying a force because the car ran out of gas. Okay, so if you think through this logically, these are the only forces acting on the car. Now, which way is the car moving? It doesn't really matter, but let's just say the car is moving, I don't know, let's make up a direction. Let's say the car is moving to the right. Alright, so what does the FBD look like? We have force of gravity going down. Okay, normal force going up, perpendicular to the surface. Notice I draw these two so that the lengths would cancel out. Now, if the car is moving to the right, which way is friction going to act? Okay, friction always opposes motion. So if the car is moving to the right, friction is going to act to the left to make the car slow down. Okay, so if you're looking just at the FBD and nothing else, okay, it would look like, maybe the car is moving to the left, but it's not. Remember, an FBD does not tell you which way an object is moving. Okay, all it does is show you which forces are acting on an object and in what direction. So the car is moving to the right. You can't tell that just from the FBD, right? But the force of friction is causing the car to slow down. Okay, so it's moving to the right. What I would say is the velocity is to the right, but the acceleration is to the left. Anytime you have velocity and acceleration in opposite directions, the object is going to slow down. Alright, so we've done quite a few examples here. We might do some at the beginning of the next class, but that should be enough for you to start working on your worksheet. Okay, so pause there if you need to add that to your notes. I'm going to make a short extra video just going over the first couple problems on your worksheet to help you out so you don't have as much to do. Just keep in mind as you're doing this worksheet, make sure you answer all the questions fully. Make sure you indicate whether or not the net force is 0 or not. Can draw the lengths and labels correctly. I'm going to do 4 problems. I'm going to make a short video going over those 4 problems really quickly. This worksheet, you're going to click on the link in Canvas to open up the worksheet, and either you can print out the worksheet if you have a printer at home, or you can just write your work on a scratch sheet of paper and then upload a picture of the work. Okay, I would highly recommend you have the Canvas Student app on your phone to do that. As always, please let me know if you have any questions, and I'll see you guys in the next video.